right. So today we're going to jump in to a little more of Newton's laws. Last time we sort of talked a little bit about um, Newton's first law, the law of inertia, and we just finished talking about some inertial reference frames. This is all sort of building up to being able to calculate forces in various situations. But what is the relationship between uh, object with mass and its own acceleration? Say I want to make an object accelerate. What kind of force would I need to apply to an object with mass in order to change its velocity? Well, that's where we're going to go over Newton's second law. Newton's second law shows a nice relationship between force, mass, and acceleration. So Newton's second law says that the force needed to accelerate an object, and I'm going to say force, so F net. So it's sometimes you see it as net, or you might see this as total. It's just how much force you add all together is required to accelerate this object the way it is, accelerating. This force is equal to the mass of the object multiplied by the acceleration. So force is a vector. Now also acceleration is a vector. These directions are important. And later on today, we're going to have a lot of good pictures and even go into some helpful diagrams. So this equation, F equals ma, is something that is very helpful and also very simple in calculating forces. Something it's very easy to memorize. Just simply rearranging it gives us, a way to find an acceleration. If we had some forces, maybe if we sum up all the forces and divide it by the mass. Right. So we have, F equals ma. Let me, just to clarify, I'll do parentheses. What does F net mean? Well, I'll say where F net, so like this total force is equal to the summation of all of the forces. So in other words, I could just say this is equal to like F1 plus F2 and so forth. All right. Applying a force to an object will cause it to accelerate. This is sort of why Newton is, he's, set the standard, trying to refine motion. He's, he saw this relationship, and he had to sort of I don't want to say invent the idea of mass, but he's had to sort of decide on a actual value, so that way it could be useful for other people. What we're getting at is that's the unit of force. I don't know when they started calling the unit of force a Newton. Unit of force is a Newton. I don't know if Newton himself labeled a unit after himself. That'd be a little weird. But for force, say I write down F equals ma again. Goes m a. This is just simply 1 Newton is equal to 1 kilogram times 1 meter per second squared. So this sort of very simple arrangement, it's all 1-to-1. Whenever you're doing your calculations, it's always important to have this in kilograms. Also important to have your acceleration in meters per second squared when we're talking about newtons of force. Okay, let me go over just a brief example now. So I think I can move it down like this. All right, so a force is exerted on a block that produces an acceleration of 5.0 meters per second squared. The block has a mass of 1 kilogram. An equivalent force is then applied to a second block. We're going to call mass 2. This has an acceleration of 11 meters per second squared. So what is the mass of the second block? Was the magnitude of the force exerted on these two blocks? I guess I forgot to write that on the 2 blocks. Okay, so let's first start out with, I always start with a picture. We have this block that is just being pushed, and it's called mass 1. Sure. And it's being pushed, or it's being a force is being applied to it in a specific direction. It doesn't appear to matter for the problem. I'm still going to make it a vector. So what is the force being applied to this block? Well, it's just force is mass times acceleration. That is just 1 kilogram times 5.0 meters per second squared. It's a very, very straightforward result you get here. So we have a force of 5.0 newtons. So we've kind of solved the second part first. Next up is, what is the mass of that second block? So we have a second block. It's of a different or unknown size or mass, but an equivalent force is applied. So we will say that F is the same for mass 2. We've already found F, the force up here. So we'll say that's F equals MA. This turns into 5.0 newtons is equal to an unknown mass, we're going to call mass 2, multiplied by this acceleration. We can at least measure how fast this block accelerates, which turned out to be 11 meters per second squared. Dividing over, we get mass 2 is 0.45 kilograms. So that makes a bit of sense, because if we have a smaller block, so M2 is smaller than M1, we have this smaller block that is less massive. That means it's going to accelerate faster. So we have this larger acceleration here than we did for that first block. So if you push a small object, it's going to accelerate quicker. So all of our values sort of look correct, and we can intuitively sort of see they are. All right. Next up, talking a little bit about the force due to gravity. In some previous problems with projectiles, we kind of just threw some acceleration is always downward, and we just sort of told you that and let you do some projectile problems. But we need to consider that something is accelerating downward. Let me move to that page before I forget to. So force due to gravity. And this. Okay, so the force due to gravity, there's this constant acceleration that is accelerating all of these objects that are on the surface of Earth downward towards the center of the Earth. So these objects have mass, they are accelerating. That means that there is this force due to gravity that is directed downward. And to keep things clear, you could label things, I'm going to say F sub G. So some people, I can also just like spell out gravity like this, but it's too much. It's too much. Sub G is mg. So instead of acceleration here, the acceleration is g itself. That's something that we've given to you. This shouldn't be too much of a surprise. What I was saying about the indices right here is that in some problems, you might have like many factors. You could just label the indices whatever you want, as long as it's clear to you. The rest I have to say about this is that, just so I have written it down once on my notes, G is equal to 9.81 newtons per kilogram, or we could say what we already know, 9.81 meters per second squared. Same value, it's just you see how the units can be slightly different if we sort of make them into a Newton It has to be newtons over kilograms. All right, so we've gone over, forces one object accelerating another object. We can, continue to classify all of these different types of forces. One object might be, pushing or pulling. But what if and I have this, force due to gravity, and it's clear if I have this projectile, I throw this ball, it's moving, and eventually it's being accelerated downward. What I want to know is, what about things that aren't necessarily moving? What if I have like a book and I throw it on a table, and the book's sitting on the table? Are there any other types of forces involved? There's force of gravity, and that's pushing down. We're just looking at the book. Why doesn't it sort of, break through the table and go like straight and dig into the earth straight down? Why is the book stopping right where it is on top of the table? Well, that's where we need to also think about what is called a normal force. So we have this book on a table. The normal force, a normal force, is a force that is perpendicular to an object's contact surface. It could be, it's typically, before I say any, of my examples, it's typically where this object may sit on top of on top of a surface. But so in this case, we have this book or, a block, and it's being forced downward. That's the force of gravity, force due to gravity, like this. And the reason it doesn't continuously move downward is because the table's stopping it. So the table is pushing up. This is the normal force. It is perpendicular to the contact surface. So here's the contact surface. Right here, it's perpendicular to that. If I wanted to be, more, if I wanted to, maybe drive that point in a little more, you could think about the forces all colliding right here, right where they're meeting on the table, like this. So the force of the book, force due to gravity, is downward, and right where it's contacting, perpendicular to the surface, that is the normal force. So that's F sub n for normal force. All right, so that's a perpendicular force to sort of a contact surface. What about, this is a flat table. What if I have, one of the legs of the table breaks and the table is sort of slanted a bit and it becomes kind of like a ramp? So we have this, block on a ramp. But, it's not, too steep of a ramp. You can have, something on an incline, and it doesn't immediately, always slide down. there's something holding it there. This is friction. This is a frictional force. So let me draw some of the forces acting on this block. Now that we know there is the gravitational force from the top of the page that is always pointing downward. So straight down. Force due to gravity. There is also, since this block is resting on a surface, it is in contact with the surface, there is a normal force that is perpendicular to the contact surface. So perpendicular would be like this way. So I'm going to try to do that. It's going to be like something like that. Perpendicular to the contact surface. Then we have this other new thing that is a frictional force. Frictional force is a force that is parallel to the contact surface. So this is where we're kind of like, we have to learn how to adjust our own reference frame a bit, tilt our head, and see that the frictional force is parallel to the surface like that. And in this case, since the book isn't moving, or this block isn't moving, the friction is pointed upwards like this. But why is it pointed upward, and why isn't it not pointing downward also? Well, that's because maybe I can make sense with just these, the arrows I've drawn. The magnitude of this, if you look up at the top, the normal force, this one, these two forces, they are equal and opposite. So they, in a sense, cancel each other out. And so there's no net force acting on the block for this top example. That's because they're pointing in opposite directions and they are the same size. However, for this, block on an incline, we have this, force due to gravity pointing downward, but it's not equally matched by something pointing upwards. This normal force is going at a slight angle. So in a sense, it has some X components and some Y component like this. So it's not completely canceling it out. This frictional force is something that will, let me, so this frictional force is something that opposes motion. And if it is pointing upwards in this direction, these two add together. These two forces add together to equally match this force of gravity. And that's why some things can just sit on top of a incline without sliding down. We're going to go, a bit more over friction later. So I would say you don't have to worry about completely grasping friction yet. But this is sort of a demonstration of how many forces can sort of be acting on one thing at once, even though this thing is not necessarily moving. In this case, since the block is not moving, all of the forces sum to 0. Okay. Next up is to forces surrounding some springs. So we have Hooke's law. Hooke's law is a very specific law. It's not too hard to grasp either. It was sort of arrived at differently than Newton's second law. Hooke's law was sort of meticulously measured out over I guess hundreds of springs, and there was just sort of a pattern that was discovered by Robert Hooke. And so he noted it down and found out that there's this sort of spring force that all springs have. If you go to the hardware store, you see a box of springs. There are some that are like already pre-stretched. They're already sort of extended a bit, and they're hard to compress. There are other springs that are sort of hard to, like they're already sort of, shrunk together. They're hard to extend. And, the real fun ones, you like think of like a slinky, the toy. There's some that stretch real easily. So this sort of behavior, sort of property of like how hard this spring is to, stretch or, contract, that is called the spring constant. And this value is different for every single spring. So, going through, like if some, companies trying to manufacture springs, they have to, do a whole set and then, test a couple to make sure they're all staying the same. Or, the spring constant isn't, wildly different from what they're saying it should be from their product. So we have, let's say we have a spring that is like kind of stretched, but it sort of rests at this position. Zoom in a bit. So this is sort of the equilibrium position. That's where it rests naturally. If you were to, compress it, it would want to go back to this spot. If you were to stretch it, it would go back to this spot. So let's actually, I have a couple already prepared, so I don't have to draw this again and again. So if we were to stretch or compress, this spring would naturally want to move back to this position. So this sort of equilibrium position right here. What we have is on all of these, I have, going to the right is a positive value. And so if we stretch this spring, this is going to be a positive X value. And the difference between the two, sort of, how you're moving this, would make this, a positive increase in distance. Looking at the compressed spring, this over here would be a negative X value. You're sort of moving it to the left of its natural, 0 point. So I could also draw the forces that's, they're trying to, the spring is trying to, move this block. So if I were to stretch out this block on the spring, the spring would try to force the block back that way. And I'm just going to say f of x because that matches the Hooke's law equation I've written. And if I were to compress the spring, the force would be in that way, in to the right. So f of x would be that way. So since we have, this, I've already labeled that right, moving to the right is positive, moving to the left is negative. So that would show that this force up here is negative. And so we can have a negative force. It all depends on where we label our coordinate system. So that's just me saying to the right is positive, to the left is negative. So force is negative, that just means that way. On this one down here, the force just happens to be positive. Force is positive. Okay. So we have a general idea of how, a spring force might work. I think we may go over this a bit more with when we get to oscillations at sort of the end of the semester. But for now, this is most of what we need for, spring motion. Anything that is sort of spring-like. Moving from springs to strings, sort of like a string or a rope, we have strings. This is just, force that is applied by using a string or rope is just called tension. And that's something that's should be sort of known already, but I wouldn't expect you to know already. There is this mass on the left that is, hanging from a string, and tension is just the definition of the force going through that material of the string or the rope. So tension is in the direction of the string. So in this case, let's draw all of the forces. We have, first off, this block is just hanging here and it's not moving. So not moving, that means there's this force of gravity trying to pull it downward. And then there is this force upward counteracting this force of gravity. So I could draw it on the side, or I could draw it on the string itself. Do that. And that is tension, T. And that is also just a force. So so I could just say T, or I could have said F of T for tension, the force of tension is just a force. So mass times acceleration as well with this. Okay, what about a block and someone or something is pulling this block with a rope, and it's on a surface, frictionless surface. Well, we have the force of gravity is always, pretty much always, pointing downward. Since this block is resting on a surface, is in contact with a surface, there's a normal force pointing upward. And let's say there's, this block is, it just happens to be being pulled. It's being pulled with a specific force through the rope, and that is a tension to the right. All right, so that's just sort of a way to think about forces in a string. They just follow the path of wherever the string is going. All this kind of leads to the next big point, or the next page, where, let me see if I can back out of this. You can see there are a lot of individual little pictures that I've drawn. And maybe, and I've also drawn a lot of arrows for forces. Sometimes that can be just a big mess of, it's just too much going on. I can't clearly see what is happening. Here, see, look at this spring, like what am I supposed to focus on? So, people have noticed that this can be a problem when doing, a specific, situation or calculation. So we have arrived at making a free body diagram. This is to sort of solve the issue of, this picture is too cluttered. I don't know what's going on. So a free body diagram, let's put a little definition at the top. Free body diagram is just a, very simplified picture, or it's a diagram that shows a simplified view of all of the forces acting on an object. So this diagram is focusing on a specific area, and it is free from its surroundings. So in the book, they give an example of a dog sled. So let me put in this dog sled. Okay. We have this dog sled now. What are the forces acting on the sled? We're only interested in the sled. Well, from before, seeing that there's, normal force upward, force of gravity downward. There's this sort of rope that's pulling that way. I don't know if this is ice or not. Maybe there's friction. The images of me drawing arrows on this picture can just confuse sometimes, and that's okay. So it's the reason we're going to simplify this image. First off, let me make a dotted line around the sled. So we're only looking at this. That is all we're looking at. Now I'm going to make a free body diagram over on the right. And that's just a, I like to make them as a block or a little square. Some people do it as just a dot. It's up to you how you want to do it. But ultimately, there is just this single point, a single little block that has all of the forces, all of these arrows, vectors sort of mapped out on top of it. So this represents everything inside of the, dotted bubble right here. So we have a force of gravity that's going down. We have the normal force pointing up. We have the force to the right that is, maybe that's a rope, maybe that's just a like a pole. We don't quite know. So I'm just going to say that's the force supplied by the dog, D. So F sub D. And it's, has a specific direction. And let's say there's no ice. I'm sorry. Let's say there's no friction. So this is on ice. So there's no friction, sort of countering, going to the left. Okay. So we have this, simplified free body diagram. The good thing about a free body diagram is I can physically draw this to scale. I could get a ruler out and map out the size of these vectors and their directions, and I could solve this just using graphing paper and a ruler. I could solve any problems like this. I could see, oh, that one, these two are probably going to cancel each other out. We'll get to that in minutes. You could do all of this stuff graphically or mathematically. So the magnitude of these, the vectors can be drawn. They can be drawn to scale. And whether you are doing this graphically or mathematically, at some point, you're going to have to split up the components of these vectors. So at the end of the day, we're again just going to be adding vectors. So in order to do that, we need to split them up into their component pieces. Let's try to keep it in frame like that. Okay, so let's split this problem up that I have up at the top. Let's split it up into its component pieces. So we're going to sum up. So summation of all of the forces in the x direction is equal to, and this is where we could look just at the free body diagram. What are all the forces involved? So I'm just going to put all of them down, and I'm going to say, what's the x component of this, x component of this, and that, and this, and that. So the force, the normal force, x component, plus the force of gravity's x components, plus the force of the dog pulling the sled, so d x. All of that is equal to, so you're here, f of x. So I'm just going to put that on the other side as, the total. It's the mass of the sled. Times the acceleration in the x direction. Okay, so looking at the free body diagram at the top, what are the x components of the normal force? So horizontal, there is none. So that's 0. And for gravity, force due to gravity, also 0. And the force supplied by the dog is going to be a positive value to the right. So I'm going to keep this positive, and it's just the force of the dog to the right. That's equal to the mass of the sled, acceleration in the x direction. From this point, you can see I can find forces or accelerations or even masses. Just for a quick example, I could rearrange as the acceleration in the x direction is the force applied by the dog over the mass of the sled. All right, so that is me just focusing on the x component. Let's focus just on the y component now. So it's going to be the same exact thing, except for the y component. So the y component, vertical component of the normal force, the vertical component of the force due to gravity, the vertical components of the force that the dog supplies is equal to the mass of the sled times the acceleration in the y direction, or vertical direction. So I am going to have to move down here. This. So we know from the problem, the problem would have stated if it is moving up or down. So we could say right out of the gates, we could say that it is not accelerating up or down. So that would mean over here, this acceleration equals 0. So this whole right side of the equation equals 0. I'll do 0. So the whole thing equals 0 like that. There we go. I can do that. So we have the normal force is, I'm going to call things moving up positive. So that's just a positive force upwards. Things moving down are negative. So I'm going to say that's a negative force of gravity downward. And there is no vertical component of force supplied by the dog. Ultimately, this is how we can sort of weed out, sort of separate these two components. In this specific case, we see that the normal force is equal to the force due to gravity. And that makes sense because they're equal and opposite, and the the sled isn't just moving vertically up or down. It's stationary on top of the ice, in the vertical direction. Okay, so that's sort of the intro example. For the rest of for the rest of my time, I'm going to do some examples, and we'll see how far we get. Okay. So starting, we just did a problem with a sled on some ice. So let's do another problem similar to that. So let me probably right about here. Okay. So a person decides to pull a sled with a force of 150 newtons at 25 degrees above the horizontal. The total mass of the sled is 80 kilograms. And what we want to know is find the acceleration of the sled, and find the magnitude of the normal force of the surface acting on the sled. Okay, so if I were to draw that picture again with the sled, we can see that, maybe the problem comes with the picture. You can see that it can become messy fairly quick. I could demonstrate by, adding some of these forces in here. So the normal force, or, start out with, we'll say that the force of gravity is down, the normal force is up. There is this sort of force being pulled at an angle by a person who is, dragging the sled, and it's at a specific angle above the horizontal. See, now this, actual image is messy. What we can do instead is make a free body diagram, something that's just, taking all of these, forces and angles and simplifying it. So let me do that over here. So let's say it's just a dot this time. You can make it a box or a dots, whatever you want. So we have the force due to gravity downward. It's a vector. We have the force going upward. It's contacting the surface, so it's force going upward, normal force. There is a force being pulled at a, obscure angle above the horizontal. So let's add the horizontal in here. So I'm going to make this a dotted line. Okay. And it's being pulled at some sort of angle, kind of like that. And that's the force of, we'll say FP for person. So the person is pulling it at this angle above the horizontal, like that. Okay. Just like that. Awesome. Something that we know that we're going to have to do. We're going to have to split this up into its components. So before I even do that, I know this is a vector at an angle, and I know I'm going to split it into its, horizontal and vertical components. So let's just do that right now. I'm going to show that this angle, this force is made of a horizontal force, FP, so the force of the person in the x direction, and a force upward like this, so FPY in the y direction. And as before, we've done this a couple times. We can see that the force person in the x direction that is adjacent to where we're measuring this angle. So that is magnitude cosine angle. Py is magnitude sine of the angle. I should put, this is force of the person, Yes. Okay. So now that we know that we're going to go there eventually. So I'm just preparing up here. Okay, we want to find the acceleration of the sled. Let's just, look at the components, and maybe we can find something. The acceleration of the sled. So maybe we could reanalyze the question. The acceleration of the sled. It doesn't say that the sled is being propelled through the air. This question is sort of letting you imply that the sled is going to slide on the ground. The person is just, holding the rope a little higher, but the sled is, sliding on the ground. So we're expecting the sled to move horizontally. So we're going to be looking for this horizontal acceleration. So find the acceleration. They could have been more specific in saying horizontal acceleration, but they're going to let you sort of reach that point on your own. So in any case, we'll split up these two components. So let's say the sum of all of the x forces, or I guess it doesn't need a vector because I'm saying horizontal right here. So we're just going to label all of the forces involved. So F in the x direction, F G in the x direction, plus F P in the x direction is equal to the mass of the sled times the acceleration of the sled in the x direction. As before, there is no x or horizontal component of these two things. So that's a 0 plus another 0. And since I knew that we were going to go here eventually, I've prepared this term for us already. So F P sub Px in the x direction, that is just the force that the person is pulling times cosine of the angle equal to the mass of the sled times the acceleration in the x direction. All right, and I believe force, we're given a force. Angle, we're given an angle. And mass of the sled, we're given a mass of a sled. Yeah. So we have everything to solve for the acceleration already. So I'm going to rearrange this right here. P. Let me clarify this is sub P. That's just to label its cosine. That's over M. When I was going through 4A, my teacher would write the indices just huge, and the equations on the board would be a total nightmare to try to follow, and it was the hardest thing to understand. So F sub P times cosine theta over the mass is equal to 150 newtons times cosine of 25 degrees over 80 kilograms. We end up getting a horizontal acceleration of 1.7 meters per second squared. Okay. This is a bit too large. I'm going to have to shrink it a bit. Right there. Now let's do the y components. So we found the result for that first one. So found it. Next one, find the magnitude of the normal force. on the of the surface acting on the sled. So we want to find this. That's what we're getting at. So summing up the forces in the vertical direction. Same exact sort of starting arrangement. Always sort of starting by labeling everything that you have. That's okay. So we know this sled isn't accelerating vertically. It's sitting on top of the ice, and its height is not changing, or its velocity is not changing up or down. So acceleration, the vertical component, is 0. Let's bring this down. So the force, the normal force in the y component is just the complete normal force. So that's just F sub n plus force due to gravity plus F sub p in the y direction. That is just F sub p times sine theta. Okay, all of this equals 0. And since we want to solve for this normal force, let's just put everything else, all of this, subtracted over. Oh, I'm sorry. This is not plus force due to gravity. It's since gravity, I'm saying down is negative. This is minus force due to gravity. Okay, so now all of this, we're going to subtract to the other side of the equal sign. Solve for the force, the normal force. Okay. And doing this, the force due to gravity, well, I'm just going to put, no, I'll go in one more step. That's just the mass of the cart, or the sled, times gravity. And then the rest is the same. So now I will just put in the values. So that's 80 kilograms times 9.81 meters per second squared. Oh, this is getting tiny. Let me. Yeah. Minus 150 newtons sine of 25. And we get the normal force is equal to 7.2 times 10 to the second newtons. And I'm going to shrink that again because I also think that's too big for the next example. So we're going to be splitting things up into their component pieces a lot. So getting used to this process of split them up, and then you fully arrange all that you have. That's sort of a good place to start, and basically any problem. Okay. Next up. Does that work? I think that'll work. Oh, perfect. Next example, we have a, this might be the last one. Maybe I could get through one more. We'll see. But anyway, this example, a 110 kilogram basketball player does a slam dunk and then hangs onto the rim. So it's just hanging there for a moment. The metal of the rim is slightly bending downward, like a spring under compression. The rim is deflected downward by 15 centimeters from its original position. Calculate the spring constant K of the basketball rim. Okay, so starting out, again, I like to draw a picture. So we have, we'll put it right here. So I'm not going to draw, basketball rim. I didn't do it beforehand, and I don't have the time currently. So I'm going to do the free body diagram version. So here is the basketball rim. Now I'll do just a tiny sketch. So basketball rim is sort of bent downward. This is the original position, and this is it sort of bent downward. It is deflected. I'm not going to do the whole thing though. So it has a force of gravity is pulling the basketball rim down. So this is the sort of the person hanging on the basketball rim, sort of the force of them. So I should say the force of basketball player, but I will say force of gravity because they are the ones being affected by gravity. Okay, and there's this normal force just sort of maintaining is allowing the basketball player to hang there without the thing breaking, countering this force of gravity. I'll call that the force of the rim is holding the basketball player up. Okay, that's just kind of how I'm going to arrange this. And we'll say that it has already moved down to a new position, but it started out up here. And it went down a little bit. So the edge of the rim is springing down a bit. And we're going to call up positive. Okay, so let's sum together all of the forces. So in this case, it's a one-dimensional problem. It's only vertical. That's all we care about in this one. So we have the sum of the forces. The force in the y direction. So that's just these two. Forces due to gravity the person being affected by gravity, plus force of the rim in the y direction is equal to the mass times acceleration of how is this person accelerating in the y direction. So since this person on the rim is just hanging there motionless, there is no acceleration up or down for that brief moment when they're just hanging off of the rim. So again, that's 0. It's not accelerating. Okay, so we have G, Y, and R. Let's actually put what these are on this next step. No, I'll go R, Y. Okay. Okay, so force of gravity is just mass times acceleration of gravity. mg, or I'll just leave it like this, mg. And let's look at how this thing is sort of behaving like a spring. So it is moving this direction. It's moving down. So it has a negative y. So it's going final minus initial, final minus initial. It will have a negative y value for that Hooke's law equation. So we know this is a spring. Hooke's law was minus ky. But what I just sort of recognized that moving down is negative. This is going to be a negative y. So instead of or let me do this, plus, I'm going to put in Hooke's law minus k y. But then since I have shown that this is going to be moving down, which is negative, this negative sign in here becomes positive. Hopefully that is clear to see. So I could just put this and it won't take up too much space. All of that is equal to 0. Finding the spring constant is just, solving for k. Let me do that over here so there's more room. K is equal to mg over y. And we know already we have all of the things we need. 110 kilogram basketball player, 9.8 newtons per kilogram. So I'm using these units because I know the kilograms are going to cancel. Over 0.15 meters. I did have to convert this to meters because the rest of the problem, Newton was kilogram times meters per second squared. So I need to make sure this value is also in meters. At the end, we get a result 7.2 times 10 to the third newtons per meter. That is the value of the spring constant on this basketball rim. Okay, so we've gone over, sort of a, introduction and then kind of a simple problem with force, springs. Next up, tomorrow, I'm going to go over a few more examples, and then we'll be finishing chapter 4. So we're going to be finishing Newton's laws. I think I might change the schedule to be, we're going to be doing chapter 5. There are a few things that I realize that are, more important that we need to cover. We're going to cover friction and center mass in chapter 5. I think that's worth going over. But we'll be finishing chapter 4 tomorrow. And for this next upcoming quiz, it'll be on chapter 3 and 4. Yeah. As always, if you guys have questions, go ahead and email me, and I'll get back to you as soon as I can. All right.